All right. How many people remember doing this last year in Science 9? Okay, good. So this will go pretty quickly then. What we're going to do is just basically go over the rules for naming the different types of compounds. We'll review the different types of compounds. And then, I don't know if we'll get to it today or not, but we'll start talking about some of the kind of levels up from where you did the level at which you did this in grade 9. We'll level up one from there, and we'll start working with something called polyatomic ions. Okay, only affects your ionic compounds, obviously, but it does make things just a little bit different. Okay. All right, so key points for today. Got to be able to identify a compound as ionic or molecular. Those are the only two kinds we'll be dealing with. Okay, and write names and formulas for chemical compounds. Right, we will only be dealing with binary compounds. That means made up of like two parts. Okay. All right, so ions and ionic compounds. Easiest way to identify whether a compound is ionic or molecular is to look for the presence of a metal. Okay, how do we know if something is a metal or not? Right, it's to the left of the staircase, okay, and hydrogen, I mean, unless it's hydrogen, hydrogen is one of those things that can go either way. How can you tell if hydrogen is a metal in a compound? If it's acting as a metal or a nonmetal, since it does kind of go both ways. Okay. The answer is metals are always written first. Okay. If you write out a chemical compound like sodium chloride, sodium is the thing in that compound that is to the left of the staircase. Thus, it is the metal. Okay. It is also written first. All right. In this compound, hydrogen is acting as a metal because it's written first. Okay. But in this compound, it isn't, because it's written second, or any place other than first. Okay? If hydrogen appears in a compound anywhere other than first, it is behaving as a nonmetal. Right? It is the only atom element that can kind of do both. Okay? And that's how you'll know whether or not. So again, metals are all to the left of the staircase on your periodic table. Okay? And obviously are all solids with the exception of mercury. Okay? Which is a liquid. All right, so ionic compounds contain both a metal and a nonmetal, so they have something from both sides of the staircase. Okay. Ionic compounds behave differently than molecular compounds for a couple of reasons. Okay. The main reason is the way that the metal and the nonmetal bond together. All right. Ionic bonds are, let's say, a little weaker, may not be the right word, but we'll say weaker, okay, than molecular bonds. Because in an ionic bond, electrons get traded. Okay, all elements are trying to be like their nearest noble gas. Noble gases are the things on the very end of the periodic table. So helium, neon, argon, krypton, xenon, radon. Okay, those are our noble gases. They have an outer shell of electrons that's full. Okay, and all the other elements are trying to get their outer shell of electrons full. It's like their meaning of life. If you're an element, you want to have an outer shell that's full of electrons. Right? If you look at something like sodium, okay, sodium as an atom, okay, looks something like this. Sodium has 11 protons in its nucleus, okay, which means it has to have how many electrons? 11, right? They have to balance out. So, in the first shell, okay, of electrons, there can be 2 electrons. And they spread out from each other as far as possible, because they're both negative and they repel each other. Everybody with me so far? Okay. In the second shell, there are 8 electrons. And they arrange themselves something like this. Okay. I mean, it isn't really like that. We know that the electron cloud model is the current model and they kind of move randomly, but this is how we represent it. All right. How many electrons do I have now? 10. So I need 1 more. So that's 1 more shell. In this shell, there's 1 electron, but the shell can hold 8. So if sodium wants to have a full outer shell of electrons, is it easier to dump 1 or pick up 7? Yeah, dump 1. All right. And that's the way it is for most metals. Their outer shells only have 1, maybe 3 electrons in them. So their shortest route to having a full outer shell is to get rid of the electrons they have. Okay? By comparison, nonmetals typically have very close to full outer shells. If we look at chlorine, okay, as an example, okay, chlorine's got 17 protons, 17 electrons, right? So if we're looking at chlorine, okay, we've got, here's our first shell, 1, 2, okay, next shell, okay, that's 10, and then 7 in this one. Okay, if chlorine wants to have a full outer shell, dump 7 or pick up 1? Pick up 1. And it's not like you can just dump them either, okay? Otherwise, yeah, it would be easy to just, see you later, right? But they actually have to go somewhere. The electrons can't just be left alone by themselves. You have to give them to somebody if you're trying to get rid of them. So these two elements get along pretty well because they have what the other needs, okay? Chlorine needs an electron, and sodium needs to get rid of one, all right? Which is why sodium chloride is a relatively stable common compound, okay? What's the common name for sodium chloride? Yeah, table salt. Okay, salt is actually a term that means any ionic compound because all ionic compounds are crystalline solids at room temperature. Okay, a lot of them look just like salt, but the crystal shapes are slightly different. All right, does that make sense to everybody? Okay, so in an ionic compound or in an ionic bond, there's this trading of electrons. The reason the ionic bonds are not as strong as the molecular bonds is because once you have a full outer shell, you sort of got what you wanted. Okay? And there isn't really any reason to stay together after that. That really sounds awful from like a sociological perspective, but don't take it that way. Okay? So there's really no, they've got what they wanted, they have a full outer shell, they separate quite easily. That's why most ionic compounds are also highly soluble in water. Okay? You put salt in water, it dissolves like that. Okay, and that's the reason for that is that they both have a full outer shell. That bond dissociates quite quickly, right? And now you've got these charged particles floating around in the solution you've made of salt and water. So there are positively charged sodium ions and there are negatively charged chlorine ions floating around. Okay, why is the sodium positively charged? Okay, anything in that column, that's the way the periodic table is organized, yes, is +1. But why, once sodium has bonded with chlorine, does it have a positive charge? Right, it's lost 1 electron. It now has 1 more proton than it has electrons, which is why it has a +1 charge. Okay, does that make sense? Chlorine has a -1 charge. It's gained. It has 1 more electron than it has protons. Okay, and that's why ionic substances or ionic solutions will conduct electricity as well. All right? If you take distilled water and put wires in it, it won't carry a current. Okay? Distilled water won't carry a current. It has no ions, no charged particles in it to allow the electrons to flow. Okay? But if you take tap water does have ions in it. Okay? It's got calcium and chlorine and fluoride and whatever else in there. Okay? And it can conduct electricity. Okay. So is everybody good with how the ionic bond works? So in an ionic bond, the electrons get traded, exchanged, or swapped. Okay, whichever way you want to look at it. When it comes to naming ionic compounds, the rules are fairly simple. You always name the metal first. You always name the nonmetal second, and you change its ending to "ide." Okay, so the name of the metal is stated in full as it appears on the periodic table. Name of the nonmetal is given an "ide" ending. So whatever it ended with before, you change it to "ide." All right, if it was chlorine, it's now chloride. If it was fluorine, it's fluoride. Okay, everybody with me there? All right. Some of them get a little trickier, like selenium. Okay, it's selenamide. All right, you're not going to get marked wrong if you don't get it. If you go selenide and I say selenamide, it's like tomato, tomato. I don't care. You did it right. Okay. In general, I don't think there's an accepted proper way. It denotes the fact that this is now a charged particle. Okay, it's part of a compound that has resulted in, like, essentially electrons being redistributed. Okay, and that's the same with your molecular compounds as well. They all end in "ide," and that states that there are electrons now being shared. Yeah. Okay, so some examples: magnesium oxide, sodium fluoride, and aluminum sulfide. Those would be ionic compound names. Okay, we're just going to stop here and give you guys your periodic tables. So on your periodic tables, guys, okay, layout should be fairly familiar to you. Okay, we got the staircase, okay, separating our metals from our non-metals, like we said before. All right, the charge of each ion or each element when they become an ion, that is, get in a compound and lose or gain electrons, okay, is listed in the top right corner underneath the molar mass or atomic mass of each one. Okay, so you can see, like, for rubidium and potassium, this whole row, it's +1. Okay, for all of row number 2, it's +2. All of row 3, it's +3. Okay, you go over to this side here, they're also listed, but a little lower down because I actually had to put them in myself. -1, -2, -3. Okay, so you can see them all written in there. Those will be important when we start writing the formulas and we have to do the drop and swap. Does that ring a bell? Okay. All right, you also have a table of polyatomic ions at the top. Yours looks a little different than this because I found a better one and I inserted it in yours, okay, than the one that's on here. Okay, everyone fairly familiar with how that one works? Okay, hang on to that periodic table. I didn't hole punch it for a reason, okay? When it gets hole punched, sometimes you mess things up on there and information gets, punched out. I would suggest getting like a page protector or something like that for it, so that it doesn't get all ratty and torn and whatever else. Okay, because you're going to use it a lot for the next month and a half or so. Okay, so like we said, we always name the metal first, we always name the non-metal second, and change its ending to IDE. All right. So remember, we have to name both ions, and this is something that's really important, okay, that people often forget. And for the first little while, I'll be lenient about it, but as we go along, I'm going to get stickier. Names of compounds in chemistry are not proper names like Jane Doe, okay, or anything like that. It is not a proper name, it is a chemical designation. Thus, it is not capitalized unless you are starting a sentence with it. Okay, in which case, then English rules override. All right, but they are not proper names, so they're not capitalized. All right, aluminum chloride, see, no capital letters in there. Okay, and I know it's a force of habit, right? Everyone wants to capitalize, seems like a name, and they end up doing it. Okay, they're all lowercase. Okay, so when using formulas, we balance charges on each ion. That's the drop and swap thing, okay, that you guys have probably done before. Yeah. Okay, we'll look at that probably a little more next week. Okay, a true compound always has a net charge of 0. The positives always have to balance the negatives, otherwise somebody doesn't have a full outer shell and there's something wrong. Okay, so charges are positive on metals, they're negative on non-metals, okay, and they're always equal to the group number for the representative elements, which is something we'll talk about next week when we talk about periodic table and electron configurations for you guys. Okay, questions there? All right. So if I have aluminum and reacting with chlorine, okay, the name of this compound is aluminum chloride. All right. Do I put in there anywhere that there are 3 chlorines in that compound? No. All right. That's another mistake that people tend to make, is they end up putting in prefixes. All right. We don't put prefixes in on ionic compounds. Prefixes are used on molecular compounds, but not on ionic. Reason for that? There's only one possible combination for aluminum and chlorine. Right? If they're going to be switching electrons, trading electrons, there's only one possible configuration for aluminum and chloride to go together. So you don't have to put in any prefixes. Everyone will know what the formula is. There's only one possibility. For molecular compounds, it is different. Because they share their electrons, they could end up in any number of configurations in any amount of numbers. All right? And then we have to put in the prefixes to tell people how many. All right, so aluminum chloride is AlCl3. Why is it AlCl3? Well, what's the charge on aluminum on your, right, it's +3, okay, and what's the charge on chlorine? -1, right? Okay, so when you do the drop and swap, right, you take the 1, you put it here, but we don't write 1s in compounds. You take the 3, and you put it down there, AlCl3. Making sense? Quick review there? All right. Now, exceptions. Okay, this is something that's probably new. You maybe didn't deal with multivalent metals last year. Is that term ringing a bell for anybody? Okay, I didn't think so. All right, multivalent metals are metals that are in what we call the transition elements. They're in the middle. Okay, these elements can lose different numbers of electrons. Sometimes they'll lose 2, sometimes they'll lose 3. Okay, some of them it could be like 3 or 4, right? But they lose different numbers. If that's the case, and I've just got, like, let's say iron and oxygen together, and I say, well, that's iron oxide, I may not be accurately communicating to somebody what compound I'm dealing with, because there's actually 2 possibilities. All right? So iron can have 2 different charges, and if you look on there, you'll see them both listed. Iron can be 2+, or it can be 3+. All right? The charge listed first is the most common charge. Okay? The charge listed second is far less common. So if I put iron and oxygen together, okay, I would say that's iron oxide. But here's the problem with that. This is iron oxide, and so is this. Are they the same? They are not. Okay, one is rust, and the other is poisonous. So if you're, doing this scientific paper and you're saying, yeah, and then I injected myself with iron oxide and I suddenly developed incredibly stellar hemoglobin or something like that, okay? And someone goes, oh, cool, and they inject themselves with the wrong stuff, they die, and it's your fault. Okay, so it's kind of important to make sure you tell them which iron oxide you were dealing with. That's why we use Roman numerals to tell them which iron you had, whether you had the iron that was 2+, or whether you had iron that was 3+. Okay, because they make different compounds. They make Fe2O3 instead. Okay, sorry. So 3 is the most common charge. My bad. I can't remember all of them. Okay. So here's what we have to do. How do I know which one to do? Okay, how do I know which Roman numeral to put in when I'm naming? Well, I look at the compound. If I look at this compound, is it possible for me to figure out which charge iron has by looking at this formula? Does oxygen have only one charge? Yeah, it's always what? It's always -2. So if oxygen's always -2, and this compound has to come out to a charge of 0, the charge on iron had to be what? 2, +2. And that's how you do it. Now I know for sure I have to name this stuff iron 2 oxide. All right, so you just have to kind of reverse the swap and drop a little bit. Okay. Same thing with this. All right, if I'm looking at this, oxygen is always -2, okay, and I don't know what this iron is. 3 times -2 is what? -6. So I have to have how many positive charges for this compound to come out to 0? I have to have 6 positives, right? So if there's 2 irons, each one of the irons must have had a charge of 3. Right? So this is iron 1, 2, 3 oxide. Okay, so you just have to work backwards a little bit. You're not going to do that often because we don't get a lot of compounds that involve multivalent metals. Okay, but it is important that you know how to do it, and that'll be something that's new for you from last year. Okay, quick review. Roman numerals are 1, 2, 3, 4, 5, 6. I don't think you're going to go beyond that for these, okay? But you get the idea. V stands for 5. Okay, questions so far? I want you to try these ones. Okay, I want you to write the names of these compounds. None of them are multivalent. Okay, there's no multivalent metals. None of these are going to need Roman numerals. Okay, we'll work on those in a minute. These are all ionic. Yep, they all have a metal first, right? Okay, so I'll give you a couple minutes here. Actually, you know what? Let's just do the first 5 for right now. Go through those, just make sure everybody gets it, and then I'll have you do the rest. So when you get to 5, stop. All right, I can see a bunch of you are already past there, so let's have a look here. Obviously, number 1's pretty straightforward because you've seen it like a million times before. Okay, but when we're following the naming rules, okay, remember that everything is lowercase. We name the metal first, sodium, and then we name the nonmetal second and make it end in "ide," sodium chloride. Okay. For question number 2, we've got K, which stands for potassium. So again, all lowercase, potassium. And then we name the nonmetal fluoride. Okay. Ends in IDE. And you can spell that without the U or with the U. It doesn't matter. It's like that, harbor, armor, right? All that American-Canadian difference in spelling. You ever notice that? Word will always correct if you try and spell it our way. Yeah. It might. Again, I'm not going to be too... I don't teach English, so my spelling's not quite as good. All right. Next one here, we've got hydrogen listed first. Does that mean it's behaving as a metal or a nonmetal? Metal. Metal. All right. So we've got hydrogen iodide. And then I've got calcium with bromine. Do I need to put anything in to indicate there's a 2 there? No. Calcium chloride. Oh, bromide, sorry. It's a good thing it's Friday. Gee. Calcium bromide. And then lastly here, we've got aluminum and astatine. Okay, or it's actually now supposed to be pronounced aluminium, but I won't do it. So, aluminum, because they've actually changed the spelling. If you get a new periodic table now, it's actually spelled aluminium. There's an extra I in there. Okay, aluminum, and this is astatide. Okay, making sense, guys? All right. Finish up the rest of them there. Okay, we'll go over the rest of them real quickly here in a few minutes. All right, let's quickly look over the rest here. You can see quite a few people are close to done here. So number 6, CS is cesium, S is sulfur. So we've got cesium sulfide. Whoop, not sluffide, sulfide. And you can spell that pH, you can spell it F, either one is fine. Okay, for number 7, we've got sodium and oxygen, so we've got sodium oxide. Again, we don't have to indicate that there's a 2 there because it's an ionic compound. That's the only possible way those 2 can go together. All right, number 8, we've got barium and selenium, so this is barium selenide or selenamide, either way is fine. Okay, number 9, we've got radium and tellurium. So we have radium telluride. Okay, number 10, lithium and fluorine is lithium fluoride. Better? Now I've got the correct spelling on there. Okay, number 11, we've got rubidium with sulfur, so that's going to be sulfide, right? Okay, number 12, right, strontium iodide. Strontium or strontium, I don't think it matters. I think it's okay, and then iodide. Okay, and number 13, calcium oxide. Okay, and 14, right, magnesium selenide or selenamide, either way. Okay, people feeling pretty comfortable with that? That's a review from last year, right? Okay. These ones are multivalent metals. Okay, so these ones will require Roman numerals. So I'll go through the first 3 here with you just to review, okay, how this works, and then I'll let you do the rest. Right? We've already looked at number 1 as an example. Okay, iron has more than one charge. It can be a 3 or it can be a 2. In this compound, since oxygen's always -2, 3 times -2 is -6. If this compound's going to have a net charge of 0, I need to have +6 from my irons. What times 2 will give me +6? 3. All right, so this is iron 1, 2, 3 in brackets oxide. Okay, for number 2, we've got cobalt with sulfur. Right? Sulfur's charge is always what? -2. Since they're 1 to 1, cobalt's charge must be +2. So this is cobalt 2 sulfide. Okay, and then number 3, we've got manganese with chlorine. Chlorine's charge is always -1. Okay, 4 times -1 is -4. So what's the charge on manganese? +4, right? So this is manganese 4 chloride. Okay, does that make sense? All right, give you guys a few minutes to do the last bit here, and that's probably all we'll get to today. All right, so on number 4, we've got copper paired with sulfur. Okay, sulfur's charge always -2, so that means this must be copper 2, right? Copper 2 sulfide. Okay, when we're looking at the next one here, we've got tin with tellurium. Okay, and there are 2 telluriums. Tellurium's charge is -2. Yeah, okay. So if this is -2, okay, and there are 2 of them, the charge on tin must be 4. So tin 4 telluride. Okay, and then the next one here, we've got mercury and astatine together. Astatine's charge is -1, so this is mercury 2. Okay, how are people feeling with that? Okay, it's not too bad. I mean, it's just a little bit of math, right? It's not too tough. Okay, so Sunday or Monday, make sure if you're not following me on Twitter that you check the website, because I will tweet the quiz on Sunday or Monday. Okay.